Okay, hi everyone. This is our first module of the recorded lectures, and what we're going to do before we start our new topics with digital control, I'm going to review the continuous time dynamic models, and we're going to look at the representation of linear continuous time systems. And specifically, we're going to be reviewing the modeling of the system using ordinary differential equations, then transfer functions, then using all integrator block diagram, and then we're going to introduce the state space representation. Now, not only we're going to be introducing all these or reviewing all these, but also we're going to be looking at how to go from one representation to the other. So how to go from ordinary differential equation to a transfer function, how to go from a transfer function to all integrator block diagram, how to go from state space representation to a block diagram, and vice versa. Okay, so to get started, as we know, in order to be analyzing or designing any control system, the first step in the design and the control of a control system is to model the system that we are trying to study. And to model the system we are trying to study, one way to model the system is to try to describe the behavior of the system using differential equations. So we can use different laws of physics, or if it is a circuit, we can use the circuit analysis laws and techniques to get a representation that relates the input and the output of the system. So for this example, let's look at a mass damper system. So let's do an example and see how we're gonna get the different representations of the system. So in this example, we're looking at a mass damper system. And if you recall, the physical system of the mass damper system will look something like this. We have a damper, and we have a mass. So this is M, and we have a force that is applied to this mass. The force is F. And this mass, before we applying the force, is at distance y from this solid surface that is it attached to. So I hope this representation is clear. We've seen this in linear control systems. So if you like a refresher, you can go back and look at that representation. So here we have the input, which is the force, and this is represented by F, and it has a units of Newton. And we have the output of our system is the position, which is y, and it has units of meters. Now we also have parameters that we're gonna need, and that is the mass, which is m, and this has units of kilograms. And also we have the damping coefficient, and this has a value of B, and it has a unit of kilogram per second. So again, we have this mass M that we're applying a force that is trying to move it to the right, and this mass is attached to a solid surface by this damper. Now, of course, as we try to move the mass to the right using this force, the damper is going to try to resist that motion. Okay, so the first step in modeling this system is to generate the free body diagram. So if I look at the free body diagram, we're going to have the mass, and we're going to have the forces that are applied to this mass. So in this case, we have the force that is applied to trying to move the mass to the right, and then we have the damping that is going to be generating a force that is equal to B multiplied by dy by dt. So basically this damper is going to try to resist the motion that is going to be generated by the force, and this resistance or this force that is generated by the damper is going to be proportional to the constant P of the damping ratio multiplied by the speed by which we're trying to move the mass. If we try to move the mass very fast, then this damper is going to generate lots of force. If we try to move the mass with a small force, and therefore we're trying to move the mass slowly, then the damping force is going to be smaller. Again, the damping force is going to be proportional to the derivative of y, which is the speed by which the mass is going to move. Okay, so again, if we look at these forces, we can now apply the Newton's second law to get the summation of the forces that is applied to this mass is equal to the mass multiplied by the acceleration. So in this situation, we can use Newton's second law and Newton's second law tells us that the mass multiplied by the acceleration, which is the second derivative of y, is going to equal the force F of t minus v multiplied by dy by dt. So this is the sum of the forces that are acting upon the mass. The sum of the forces is going to equal the mass multiplied by the acceleration. Okay. So if we look here, we see that we obtained the first representation of this system, which is the ordinary differential equation. And in this case, this is a second order differential equation. So again, the first representation, so the system is described by a second order differential equation. And this equation states that the mass multiplied by the acceleration, which is the second derivative of y, is equal to the force minus the damping force, or we can write this as the mass multiplied by the acceleration plus b multiplied by dy by dt is equal to the force that is acting upon this mass. Okay, so this is the first method of representing a system, ordinary differential equation representation. So this is the first representation. Now, in order to solve for the output, which in this case is the displacement y, we need to know the force F of t, and we also need to know the initial conditions. So to solve for y of t, given the force F of t, we need to know the initial conditions. We need to know initial conditions. And in this case, we have two initial conditions. We have y of 0 and we have y dot of 0, the derivative of y. Okay, so this is the first representation, which is using the ordinary differential equation. If we have physical system with motion, we apply the physics laws, Newton's laws to the object we're trying to study. If we have an electrical circuit, we apply the laws, the Kirchhoff voltage law, Kirchhoff current law, superposition, etc., to analyze the circuit and get a relationship between the input and the output. Okay, so what we're going to be looking at next, so let's call this the first representation. Let's call it A. And what we're going to be looking at next is what happens if we apply Laplace transform. If we apply Laplace transform, so we can use Laplace transform and if we apply the Laplace transform, if we use Laplace transform, we can obtain the transfer function. a transfer function representation of the system. So in this case, if I look at this differential equation, applying or taking the Laplace transform of equation 1, so we're going to call this equation above 1. So take Laplace transform of equation 1, and if you do that, the Laplace transform is going to be the mass multiplied by s squared multiplied by y of s minus s multiplied by y of 0 minus y dot of 0. This follows directly from the properties of the Laplace transform. If I take the Laplace transform of a second derivative, is going to equal s squared multiplied by y minus s multiplied by y of 0 minus y dot of 0. Okay, so then we have plus b, and here we have a first derivative. If I take the Laplace of that, is going to give me s multiplied by y of s minus y of 0. And again, this follows directly from Laplace properties. And all this is going to equal the force f of s. Now notice here we use capital letter for y of s, and for f of s, while y at 0 and y dot at 0 is small letter, because these are the initial conditions. Okay, so what we can do is we can sum the terms that are similar together. So I can take y of s here, and this gets multiplied by m multiplied by s squared plus b multiplied by s, and this is going to equal to m multiplied by s plus b multiplied by y of 0, and also I have a term that is m multiplied by y dot plus m multiplied by y dot of 0, and then I have plus f of s. So I have ms squared plus bs multiplied by y of s, then I have the terms that are coming from the initial conditions, and then I have the force f of s. Now what I can do is I'm going to take y of s and divide by the term that multiplies y of s. I'm going to get y of s equal to 1 over s multiplied by y of 0 plus m multiplied by y dot of 0 divided by ms squared plus b multiplied by s, and plus I have 1 over ms squared plus b multiplied by s multiplied by f of s. Okay, I mean, notice here I have ms plus b, and here I have ms squared plus b multiplied by s. So I can take the s as a common factor, and then ms plus b will cancel with ms plus b. So hopefully this is straightforward. Okay. So if I look here, this is the transform of the response that is due to initial conditions. This is transform of response due to initial conditions, and here I have the transform of the response that is due to the input. Okay, so in order to obtain the transfer function, I have to set all the initial conditions to 0. So if I set all the initial conditions, I'm gonna get the transfer function between the output and the input, and in this case I have to set y of 0 and y dot of 0 to 0. The first two terms on the right are gonna cancel out, and what I'm gonna end up with is only the last term on the right, which is 1 over m squared plus bs. So therefore the transfer function is obtained by setting the initial conditions to 0. And therefore, in this case, I'm going to have y of s divided by f of s is going to equal to 1 over m multiplied by s multiplied by s plus b over m, which is ms squared plus b multiplied by s. Same thing. Okay, so this representation is the second representation that we are introducing, and we refer to this as the transfer function. So this is the transfer function representation. Transfer function representation. And we're going to call this number 2. Okay. So again, keep in mind that in order to obtain the transfer function, we set the initial conditions to 0. Okay, the third representation that we're going to look at is the all-integrator block diagram. All-integrator block diagram. And let's see how we can obtain the all-integrator block diagram representation. The first thing we're going to do is we're going to solve for the highest order derivative. Solve for highest order derivative. So in our equation above, the highest order is a second order, and the second order dy by dt squared was equal to negative b over m multiplied by dy by dt plus f of t divided by m. Let's call this equation 3. So again, we solved for the higher order derivative. We put it on one side, and it is equal to, we move all the other terms to the other side. So then what we're going to do is we're going to construct a chain of integrators whose input is the highest derivative of y of t and whose output is y of t. So this is the first step. The second step is we construct a chain of integrators whose input is the highest derivative of y of t and whose output is y of t. So in this case, the highest derivative is y double dot. 2 dots means the second derivative. And then I'm gonna apply this to an integrator. So this is an integrator. And if I do that, I'm gonna get y dot. If I integrate this y double dot one time, I'm gonna get y dot. If I integrate y dot again, I'm gonna get y of t. So again, we started with y double dot, we integrated once, we get y dot, we integrated it again, we get y of t. Of course, here we have the initial condition, which is y dot of 0, and here we have initial condition, which is y of 0. Okay, so after we do that, we can complete the all integrator block diagram by noting that the highest order derivative is specified in this equation. So I have y double dot, but y double dot is given by equation 3. So therefore, what I can do, I'm going to take this again, I'm going to just repeat it, y double dot, I have integrator, I have integrator, I have y of t, and now I have y dot here. And if I look at the equation for y double dot is equal to the force divided by m. So therefore I can take f of t and then just apply it to, or multiply it by 1 over m. And then also I have to add to that negative b over m multiplied by y dot, or dy by dt, which means I have to take y dot here, I have to multiply it by b over m, and then I have to add it to the other signal. Of course, I need a negative sign here because I have a negative sign in the equation. So if I look here, I have y double dot is going to equal f of t multiplied by 1 over m, and then I'm going to have minus b over m multiplied by y dot, which is exactly what I have in equation 3. Of course, I can have here also y dot of 0, the initial condition, and I have y of 0 initial condition here. This representation, we call it all integrator block diagram. So this representation is the all integrator block diagram. And we're going to see in a minute why this representation is useful. Okay. Now we can also obtain this diagram from the transfer function. So if I look at this representation here, I can also write this as f of s and then multiplied by 1 over m, and then I can write this as 1 over s plus b divided by m, and then I have 1 over s, and this is going to give me y of s. So if I multiply these, 1 over m multiplied by 1 over s plus b over m multiplied by 1 over s, I'm going to get again the transfer function that I obtained here. This is nothing other than this transfer function that I have here. Okay. So again, I can take this transfer function, y of s is equal to f of s divided by m multiplied by s multiplied by s plus b over m. I can break this into 1 over m, 1 over s, 1 over s plus b over m. So again, this will give me this representation or this diagram. Now what I can also do, I can write this. This is equivalent to writing this like this, f of s, this is 1 over m. Now this 1 over s plus b over m, I can write it as follows. This is 1 over s, and I can bring a feedback here and get b over m, and this is a negative feedback, negative, positive, and then I have 1 over s, and I have y of s. This is if I take the equivalent of 1 over S, this is G, and H is B over M, is going to give me 1 over S plus B over M. Okay. Again, the equivalent of this on the side, this is G over 1 plus G multiplied by H. So therefore, this is going to equal to 1 over S divided by 1 plus 1 over S multiplied by B over M. I can multiply the numerator and denominator by S. I'm going to get 1 over S plus B over M, which is what we obtained here. So again, anytime I have 1 over S plus B over M, I can represent it with the feedback loop that I have here. Okay. So now I can take the inverse Laplace transform of this representation that I have here, and that will give me the same representation that I got using the all integrator block diagram. So if I take this and take the inverse Laplace, I'm gonna get the all integrator block diagram representation. 1 over S is going to become an integrator. 1 over S is going to become an integrator. Okay. So this is the third representation that we're reviewing. We're doing all this to get to state, or the fourth representation, which is the state space representation. So D, as we will see, there are many advantages that are gained by expressing a high order ordinary differential equation as a coupled set of first order differential equations. So many advantages are gained by expressing higher order ordinary differential equation as a coupled set of first order ordinary differential equations. And this resulting representation is referred to as state space model. State space model. Now, as we will see, this state space representation gives us significant insight to the process dynamics. And of course, it facilitates the computation and the solving of the output of the system. So therefore, the fourth representation that we're going to be looking at is the state space representation. And let's have some formal definition. A state space model is a coupled set of first order ordinary differential equations that describe the dynamics, the dynamic behavior of the system. And we're going to be using state space representation throughout this course. Now, I know in the previous course, in the control systems, we just introduced the state space representation. But in this course, we're going to be using state space representation throughout the semester. Okay, so how do we obtain the state space representation? Because there are different methods for getting the state space representation. One method is to first construct an all-integrator block diagram of the system, and then the output of each integrator is defined as a state variable. So to obtain state space representation, we construct the all-integrator block diagram the output of each integrator is defined as a state variable. So again, let's look at the example we just did. We have f of t, then we have a constant multiplied 1 over m, we have the feedback loop, we have an integrator here, we have a constant b over m, and this is positive, negative, and then we have an integrator here, and we have y of t. So this is the all integrator block diagram. What we're going to do is we're going to come to each integrator and each integrator output. So again, everything is going this way. So the output of this integrator is x, we're going to call it x1. The input is going to be x1 dot. I'm going to come to this integrator. I'm going to call the output x2. The input is going to be x2 dot. So again, two integrators, the output, I could, of course, the order doesn't matter. I could have called this x1, x2, or I could have called x2, x1, and x1, x2. The order does not matter. So in this case, I have the integrator on the right. The output is x1, the input is x1 dot. The second integrator, the output is x2, the input is x2 dot. Now what I can do, or what I can write, if I look here, I notice that x1 dot is the same as x2. So I can, looking at this block diagram, x1 dot is equal to x2. This signal is the same as this signal. And also I can write x2 dot. x2 dot is equal to, I can write it in terms of the input and in terms of the other states in the system. x2 dot here is equal to the force multiplied by 1 over m, so the force divided by m, and also it is equal to x2 multiplied by b over m with a negative sign, so minus b over m multiplied by x2. Now these two equations are referred to as state equations. Now also, if I look here, I notice that y of t is just equal to x1. x1 and y of t are the same, so I can write here y of t is just equal to x1. Now we call this the output equation. Now notice here, I write the derivative of the states in terms of the states, and also I write the output in terms of the states. So again, x1, x2 are the states, and I'm writing x1 dot and x2 dot in terms of these states, and also I'm expressing the output in terms of the states. Okay. Now in general, For the state space representation, in general, we denote the input as u of t. So in state space representation, we denote the input as u of t. So in this case, u of t is equal to the force that we applied, F of t. And we can express the state space model in matrix equation. So state space models are often written as matrix equation. So therefore, I can write these two equations that I have above, or the equations that I have above, as the following. x1 dot, x2 dot is equal to, in terms of x1, x2 plus multiplied by u of t, and x1 dot is equal to x2, so therefore I have to put 0 here and a 1 here. If I multiply, 0 is going to multiply by x1, 1 is going to multiply x2, I'm going to get x1 dot is equal to x2. And also x1 dot does not depend on the input, so therefore 0 multiplied by u of t. Now x2 dot is equal to negative b over m multiplied by x2, and it does not depend on x1, so therefore I can write 0 here multiplied by x1 and negative b divided by m multiplied by x2, and then I have dependence on the input on f of t, it multiplies it by 1 over m. So 1 over m multiplied by u of t. Similarly, I have y of t. I can write it in terms, I'm going to write it also in terms of x1 and x2. And to write it in terms of x1, x2, y is just equal to x1, so therefore I have 1 here and a 0 here. Y is going to equal 1 multiplied by x1 and 0 multiplied by x2, therefore y is going to equal to x1, which is what we have in the equations above. Okay, so often we write the state space representation. So this last representation, the equation can be written compactly as the following. X dot is equal to a multiplied by x plus b multiplied by u, and y is equal to c multiplied by x, where x of t is equal to x1 of t and x2 of t. This is the state vector. So each one of these is a state. x1 is a state, x2 is a state. And then x dot is equal to x1 dot of t, x2 dot of t. This is the derivative of the state vector. And a from above is just equal to 0, 1, 0, negative b over m. And this is called the system matrix, or referred to as the system matrix. And b is equal to 0 and 1 over m. And then we have c is equal to 1 and a 0. because all of these are matrices, even though I don't have square brackets. But this is a matrix, this is a vector, and the same thing here. This is a vector. Okay. Now, and also one thing that we did not write here is x of 0. So we can add also here that x of 0 is equal to the initial conditions, which is x1 of 0 and x2 of 0. So these are the initial conditions. Okay, so in order to solve for the output y of t, we need to know both y of t, u of t, sorry, the input, and we also need to know the initial state vectors. So let me just write this down. So to solve for y of t, we need to know the input that we're applying. We need to know u of t, the input, and we need to know the initial state vector, x of 0, which is equal to x1 of 0 and x2 of 0. Okay, so I'm gonna stop here, and in the second module we're gonna look at the state space model, and we're gonna look how to convert it to an all integrator block diagram, and we're gonna also be looking at the state, how to take a state space model and obtain a transfer function from it. Okay, thank you everybody.